Can you hear me? That's right. Well, I'm Fabricio, and I'm from University of São Paulo in Brazil. I would like to introduce you OpenGPU, and first the motivation. Well, developing an OpenGPU is a very cool thing, so I think it's a good reason, but we have more. We need open hardware for new tools, methodologies, development, and IP cores. Free access to knowledge and technologies, and a complete system-oriented GPU implementation. That's because, as far as I know, the current GPU implementations that are open, they are very specific. They don't get the entire system. So you develop only a part and run it in a more simple system. But one of the motivation is to develop a complete system running in one platform with software, with the hardware, and with the firmware to integrate everything. Well, there are some very important applications when you have an open GPU that are new methodologies for hardware development, hardware test benches. You could take your IP and put in a real system or to simulate a real system. Specific fixed functions about video codification, major processing, and even, I don't know, using GPU, you can get that thing too. Well, we have implementation. It is running. It is very simple, but it runs on Linux. And using the software stack of Mesa 3D, the Gallium soft pipe. Soft pipe is a driver that runs over that runs on Gallium. It is very accurate, not fast, but very accurate about OpenGL implementations, specifications. And we have immediate graphic output because it is entirely on software. And that's very important for what we have later. It is compatible with OpenGL. The version 3 is not a restriction. This is just for it is running. That's good, that's good. Okay. Just say, okay. We don't have controls, okay. It's a common message, it's okay. So it is the demonstration, okay, we are trying to set up it. And the hardware part, we have a functional and a synthesizable rasterizer. It is very simple for those who know the graphics pipeline. It is a small part, but it is important, and it is fixed. It doesn't depend on shaders or processing on the real time. You could just make the hardware and put it to run. So it is expansible to other important hardware parts, because I think that in the current stage, the most important thing it is an environment to develop hardware and the software associated to it. Well, the current platform, just for testing, is an SoC board from TerraSeq, the DE1 SoC board. It has a Cyclone 5 from Altera. It already provides a complete development system, and it is very interesting because we can, with a SoC board, we can have, in this case, a Linux environment, so we can configure everything and transfer all your data to the hardware inside the FPGA. You don't have to put bridges or communicate with USB, PCI, or anything like that. It is much more easier. But it is not restricted to it. You can get a non-SoC board, a complete FPGA without, in this case, an ARM CPU, and develop it, transferring the data through it, but it's not a restriction. It is licensed under the Apache 2. I think it is a good licensing for this case. And it is open, so I did this work for my final work in the undergraduate course. And that time I could not release the code, but now it is ready to the community. And here we have the graphical synthesis of what I said before. And we have the SoC board, the CPU and FPGA part connected by the RAM system. And Mesa 3D runs entirely on the software side. And over it, we have the Gallium and the OpenGPU driver. Because Gallium is much more easier to develop the driver. But you could just take the Mesa 3D framework and develop it over it. So here are the current implementation. That driver is represented here, and OpenGPU driver is basically a soft pipe from Gallium framework, and without some modifications. So instead of processing everything on software, we take the data flow and the part for rasterizing process, and we transfer the triangles and coordinates to the hardware rasterizer inside FPGA, and process it and take back the quad fragments. Quad fragments are basically the pixels processed about the triangles. No? So here, just for demonstration, if anyone wants, I can show in my computer the diagram. But basically, I use the data path control approach. That's very common for hardware development. And here are the state machine flow. Just one time. It is very simple, but it demonstrates the functionality and the approach. And here, the demonstration. So, well, I am just taking the environment to take the correct libraries and using the FPGA in this step. Now I run a common application using OpenGL. So what we have now is this graph is being output by the hardware part. I can change on the fly the configuration. We can use entirely software or use the hardware implementation. I will step that and just change to C. This is hardware. This is the original software implementation. This is the original software implementation, and that is a software implementation too, but with the same logic used in hardware. Now hardware again. It is pretty simple, but took me something like 8 months to achieve this state. Hey guys, can you presentation? Thank you. Well, here some information. Important thing: the rasterizer used just only 847 LUTs. It's small footprint, but it can be more optimized. But it is not the focus right now. And complete SoC uses much more, but it's for the VGA hardware, for the memory system. There's a lot of things in a SoC system you need to set up before doing things. But in this platform, it has a lot of space, something like 85,000 of LUTs. And I think the principal objectives for this project is, well, it is open hardware. It must be easy to develop because today, well, we know how to develop hardware, we have the tools, but it's not so easy for some situations. And the next steps, I think it's important. Well, today we don't have a DMA approach. I was developing this some days ago, but it wasn't ready for show. Shader development, I think it's a good thing to follow now. It's a good way. And this is very hard because shader needs you to have CPUs, a lot of CPUs inside the system, the cores. You know. And for the runtime conversion of instructions of the machine, I was thinking use the LLVM for converting the shader language to the specific hardware instructions when we have actually hardware CPUs, hardware cores implemented. Video codification framework to simplify the development of video hardware, video codification, and optimize the software stack, because today software pipe is not that good for graphic pipeline. It is very accurate, but it could be much better. But it's hard work that we need to have before having an optimized approach. Well, I am Bachelor of Electrical Engineering. I took my degree in University of São Paulo, and I really like open source and hardware. I think it's very cool. And contact me. Now I'm open to questions. Open to, if you want to have questions. Yes. Excuse me? Excuse me, I don't. GitHub. Ah, okay. Here. More questions? So I think it's that. Thanks for coming, and that's it.